First, I would like to thank the organizers for giving me the chance to speak at this conference. Today, I would like to talk to you about our molecular spintronic devices and how their unique properties can increase the efficiency of neuromorphic computing. Let me first briefly introduce the devices I'll be talking about. Molecular spintronic devices are made of two ferromagnetic electrodes that sandwich an organic semiconducting layer. Originally, the rationale for using a molecular semiconductor was that since it is made of light elements with low spin-orbit coupling, it causes little spin scattering, so that the spin-polarized current injected by the ferromagnetic electrodes can be carried over relatively long distances. In the case at hand, the ferromagnetic electrodes are thin films of lanthanum strontium manganese oxide and cobalt. In addition, theory and experiment confirm that the insertion of a tunnel barrier between the ferromagnetic electrodes and the molecular layer is beneficial to spin injection. This is a typical magnetoresistance curve. The resistance is maximum when the magnetizations of the electrodes are oriented parallel to each other, while the resistance is minimum when the magnetizations of the electrodes are oriented antiparallel to each other. Such magnetoresistance indicates that the spin-polarized current is flowing between the electrodes. These devices can also act as resistive memories. As you can see, when the voltage applied between the electrodes is set from 0 to increasingly negative values and then back to 0, the conductance of the device changes. The current voltage characteristics shows that the conductance can be decreased by the application of a negative voltage pulse, while it can be increased by the application of a positive one. Importantly, the changes are non-volatile and reversible. What makes these devices unique is the interplay between the resistive state and the magnetoresistance. As you can see, the magnetoresistance is maximum when the conductance is greatest, and it decreases as the conductance becomes smaller, eventually vanishing. In order to affect a change in conductance, the applied voltage needs to exceed a threshold. For example, the 100 millivolts applied to measure the magnetoresistance do not change the conductance of the device. The fact that the magnetoresistance can be measured at low voltages, such 100 millivolts, is suggestive that the usual picture of the energy balance alignment for these devices is not adequate to explain the observed behavior. As you can see, for hole and electron injection in the organic semiconductor, there are energy barriers in excess of 1 electron volt, so that charge injection into the molecular semiconductor should be much smaller than the one observed. Another unusual fact observed in these devices is that there is no sign of spin precession in the molecular semiconductor. Usually, carriers are injected into the organic semiconductor with the spins oriented in the plane of the device, and the magnetic field applied perpendicular to the device should cause the spin to precess. Since transport in the organic semiconductor is incoherent, the precession should cause dephasing, and thus all information on the original orientation of the spins should be lost. Therefore, with a magnetic field applied perpendicular to the device, the state with the magnetizations of the electrodes parallel to each other and the one with the magnetizations prepared in the anti-parallel configuration should show the same conductance. Instead, what we observe is that the two magnetoresistive states survive the application of the perpendicular magnetic field. Therefore, no spin precession occurs in our devices, contrary to what is expected. In order to gain more evidence on the workings of our devices, we carried out in operando X-ray absorption spectroscopy. This allowed us to access the chemical changes that took place when the conductance state of the devices was changed. When the device was set in a high conductance state, we detected a smaller amount of oxide in the aluminum oxide barrier. When the device was set in the low conductance state, instead, the tunnel barrier was more oxidized. This provides a clue on what is going on inside our devices. Oxygen moves from the aluminum oxide into the molecular semiconductor and or vice versa, depending on the sign of the applied voltage. To explain the evidence I described, we turned to an impurity band model introduced by Professor Jigang Yu. In this model, conduction happens through impurity energy levels in the gap of the molecular semiconductor, represented by red dashes. Based on the changing amount of oxygen inside the aluminum tunnel barrier, we ascribe the impurity levels to oxygen, which is present as a mobile species both in the molecular semiconductor and in the aluminum oxide tunnel barrier. When a sufficiently positive voltage is applied to the bottom electrode, oxygen is driven from the aluminum oxide barrier into the molecular semiconductor. The tunnel barrier becomes more leaky, that is, more conductive. At the same time, the greater concentration of transport levels in the molecular semiconductor decreases its screening length, thus narrowing the Schottky barriers between the electrodes and the organic semiconductor. This too contributes to increase the conductance of the device. On the contrary, the conductance decreases if a sufficiently negative voltage is applied to the bottom electrode. In this case, oxygen is driven from the molecular semiconductor into the tunnel barrier, increasing the width and decreasing the conductance of the Schottky barriers and making the tunnel barrier less leaky. The model reproduces successfully the interplay between conductance and magnetoresistance, and it captures the physics too, since with just one parameter, that is, carrier density, it accounts for both the conductance and the magnetoresistance simultaneously. The impurity band model explains also the absence of spin precession in our devices. With a sufficiently high concentration of carriers, an exchange interaction sets in between the carriers. This allows change and spin transport to become decoupled, and spin is transported by spin waves. With a carrier concentration greater than about 3 × 10⁻17 per cubic centimeter, the spin diffusion constant due to the exchange interaction exceeds that due to the carrier hopping by several orders of magnitude. Thus, spin transport happens too quickly for spin precession to occur. This explains why no spin precession is observed in our devices. Now let's turn to how the properties of the molecular spintronic devices can be employed in neuromorphic computing. Let's briefly introduce what is it that we seek in a device in order for it to be useful in this application. There are many different approaches to neuromorphic computing, and the one I am going to describe is just one of many. As you probably know, a neuron can be conceptualized as a cell with many inputs and one output. The output is provided, that is, the neuron fires when the strength of the input exceeds a threshold. A crucial aspect of this process is that inputs are not equally important, with some having more weight than others. This weight is encoded in the synapse. Each input is multiplied by the corresponding synaptic weight, which in our case corresponds to the conductance of the device. The sum total is then compared with the threshold, and if it is exceeded, the output of the neuron is activated. Basically, the operation carried out is a vector times vector multiplication, and if the same inputs are connected to several neurons, as is often the case, the operation is vector by matrix multiplication. Another hallmark of neuromorphic systems is their ability to learn. This is provided by the possibility of adjusting the synaptic weights so that a specific input gives the desired output. So the two basic needs for neuromorphic computing are the ability to perform vector times matrix multiplication and to have adjustable synaptic weights, that is, conductances. Let's see how molecular spintronic devices can provide both of them. In our instantiation of a synapse, as we said, the synaptic weight is embodied by the conductance of the device. The learning ability is represented by the possibility of changing the conductance in a controlled manner. Here we show that by the application of a suitable voltage pulse, the synaptic weight can either be increased or decreased controllably. Importantly, the voltage pulses are not dependent on the conductive state of the device. In this way, you don't need to know what the state of the conductance of your device is. For example, if a learning algorithm tells me that I have to raise the conductance, I simply apply a positive voltage pulse. The devices are resistive memories, but also spintronic devices. When in the low conductance state, that is low synaptic weight, the conductance is not affected by the applied magnetic field. On the contrary, when the device is in the high conductance state, it can be controlled also by the magnetic field. This means that high conductance devices, that is high synaptic weight devices, can be selectively targeted by the magnetic field and can be made more conductive still while leaving the low weight synapses untouched. Professor Robert Legenstein of the Graz University of Technology simulated this behavior in a reinforcement learning algorithm. We modeled the magnetoresistance versus conductance behavior of the devices with a simple power law. This update law was used in a test reinforcement algorithm to learn the task OR and AND. As you can see, the use of this update law in the learning algorithm sped up the learning process. So we have demonstrated that our molecular spintronic devices can embody the plasticity of synapses that is necessary for learning, and that the magnetoresistive response can speed up the learning process. Let's now turn at the other operation we are interested in, the vector by matrix multiplication. To perform vector times matrix multiplication naturally, the spintronic devices can be fabricated in crossbars, in which several top electrodes cross several bottom electrodes, and the active device is at the crossing area. In this example, there are a total of 12 active devices, each representing a synapse. In this example, each blue bottom electrode represents an input. The input can be provided as a voltage, for example, 1 volt to represent the 1 bit and minus 1 volt to represent the 0 bit. The neurons instead are represented by the gray top electrodes, and the output is represented by the current flowing through a neuron. Here, for example, the output O2 of neuron 2 is measured by an amperometer at the same time as the input voltage is applied. So by applying the input voltages and by reading the output current, we have effectively performed the vector by matrix multiplication, where the matrix is the matrix of the synaptic weights, that is, of the conductances of the devices. Let's now turn to the learning process. For the learning process, a voltage pulse must be applied to the synapse whose weight we want to change. For example, the one here circled in red. In order to reduce crosstalk between synapses, half the voltage is applied to the top electrode and the other half is applied to the bottom one, so that only the selected device feels the full voltage pulse, while the remaining ones are only subjected to half the applied voltage. Crucially, the half voltage is smaller than the threshold voltage, so that only the selected synapse is affected by the voltage pulse, while all the remaining ones are left unchanged. We have fabricated such crossbars experimentally. For example, in this 3x4 crossbar, we measured the conductance of each device. We singled out the device circled in black and set it in a high conductance state by applying a positive 3-volt voltage. Being in this state, it showed a magnetoresistance. We then applied a negative 3-volt voltage to the same device. As you can see, the conductance of the target device decreased, while the other ones were left almost unaffected. Being set in the low conductance state, the device showed no magnetoresistance. So we demonstrated that our devices can work in crossbars, that the conductance of the devices can be modified selectively, and that the magnetoresistance behaves as expected. I also hope to have shown to you that an update rule for the synapses that includes the magnetoresistance in the learning algorithm can speed up the learning, so that resistive memory devices that also have a spin bar behavior possess a unique advantage for neuromorphic applications. With this, I would like to conclude and thank you for your attention.